Welcome back. Let's continue with cloud storage. I think I already asked you the question that was the one about the data shapes. Here's the thing. I told you last time about some use cases that we have for big data, right? The DNA, the CERN high energy physics data, and I gave you also the example of the Sloan Digital Sky Survey, SDSS, which is trying to store data about the sky. All the stars and galaxies and nebulas and black holes and everything that we can find in the universe. Now, I actually looked at it out of curiosity. I wanted to know how much data is there in there, how many files, how many directories. And this is what I found out. There is 273 terabytes of data in 680,000 directories in 176 million files. Now, as you might have guessed, that doesn't fit on your laptop, obviously. So you cannot just put it in PostgreSQL on your laptop. And the number of files and directories is also very likely to be beyond what your laptop has. Maybe you're going to have a few tens of thousands, maybe hundreds of thousands on your laptop, perhaps a million for some of you, but 100 million, I think you're nowhere there on your laptop, right? So that raises the question, how do we deal with 273 terabytes of data? Because now that these people worked hard for years accumulating that data, we need to query it, right? So how do we deal with that? So again, we looked at relational databases in the brush-up, which might be the first natural ID that everybody has. But a relational database system, at least the ones from the 70s, and that includes PostgreSQL, they fit on a single machine. Not multiple machines, just one. So it's constrained by the size of your machine, right? Doesn't go beyond 26 terabytes on a single drive. Maybe you can have a second drive on your machine to expand a bit, but still doesn't fit on a machine. Petabytes do not fit on a single machine. We are not even in the petabyte range here with the astronomy survey, but we can also have petabytes of data, doesn't fit on a single machine. We don't want to reinvent the wheel, of course, because we could invent new things, but I have good news is that 98% of what we invented in the past 50 years and even in the past millennia can and will be reused. We'll be very careful in this course to learn the lessons from our ancestors. So good news for you, selection, projection, grouping, sorting, joining, this is not going away. We're going to have that also at the very large scales. It's implemented differently, but we're going to have that. The notion of a language, SQL, declarative, functional, the optimizations, the query plans, that's the Greek letters, the indices, and so on, also not going away. This is all here to stay, just going to working on large scales. Tables, rows, columns, primary keys. Remember the social security number that identifies a person, primary key. That's also not going away. However, and that shouldn't be new for you because I warned you about that. What's going away is the consistency constraints. We are throwing away the tabular integrity. Relational integrity is the other name. We can have different columns in different rows. We are throwing away domain integrity. We don't even require that that the values in the same column are of the same type. We are throwing away atomic integrity. That's the first normal form. We allow tables in tables in tables in tables. We're even throwing away the Boyce code normal form by having a single big table rather than splitting them. So we're throwing all of that away, and instead we are allowing for the data to be heterogeneous, nested, tables in tables in tables, and denormalized, meaning that we have a single big data sets rather than multiple data sets. Another word for that is just a big mess, right? We are allowing for a big mess. Why do we do that? Because that's the real world. The real world, when you gather data, is going to be a big mess. But once you have a big mess and technologies to handle the big mess, then you can clean it up and you can change your data and prepare your data, for example, for machine learning and so on, right? But now we have an ecosystem that is resilient to messy data. And we're going to see that we can deal with all of that without any problem. Which is the time now to ask you a question. We still have 5 minutes until the break, so I'm going to ask you 2 questions, actually. 2 questions. No, not that one. Let me think. This one. So this is a question about technological choice to scale up with the production of electric cars. So how do you think that the price of batteries managed to be lowered by Tesla? How do they do that? Did they completely redesign the car engine to consume less power? Or did they completely redesign a battery that has more range, the BFB, or by assembling plenty of cheap, widespread, standard 8650 batteries? Or you're not allowed to tell us. Yep, you got it correctly. So the way it's done is taking plenty of small cheap batteries and putting them together as a big pack of small cheap batteries. So next question for you. What is there in a data center? Is that top secret? Is this a really big machine that has 1 petabyte of memory, 1,000 cores in the CPU, 100 petabytes of a single disk? Or is it plenty of small cheap machines? Or is it a giant quantum computer with an array of 54 bits? Qubits, Sycamore. Well, Sycamore was supposed to be 54. Now they say 53, but that's because one of them broke. So the original had 54. Okay, let's see at your answers. Right, maybe the question before that helped a bit, but you are absolutely correct. In a data center, there are plenty of cheap machines. That's all there is in a data center. So I'm sorry if I spoiled it, because you might have thought of a data center as a fancy, something very fancy. But this is really just a high number of small and cheap machines. So it's not the supercomputer that you might imagine, like the gigantic thing that we see in movies. All right, let me get back to the slides. If I did everything correctly, it should be right there. All right. So we have the break in 2 minutes. In 2 minutes, I think I will manage to show you the stack. What is the stack? Well, this is how computer scientists think. They like to make things modular, right? It's like in a house, you have the electricity, the plumbing, and so on and so on. So in this lecture, we're going to take the monolithic relational database, monolithic just because it's a single block installed on a single computer, and we're going to turn it into a technology stack that we call the big data technology stack. What is there in the stack? There's all of that. There's a layer of storage. We're going to start today with storage, in particular S3 blob storage. Next week, HDFS, which is a distributed file system. Then we look into how to encode the data, actually maybe not much because it's also a bit boring. So, but this is how you encode text into bits, zeros and ones. So there's ASCII, UTF-8, these are just the fancy names for doing that. Then we're going to look into syntax. CSV, you probably know because these are files for tables, but we'll look into XML, JSON for trees, and some others. We'll not look into them because it's out of scope, but there's plenty. Then we're going to look into data models. What is a data model? It's like a physics model or a machine learning model or whatever. It's just that it's modeling data. The relational model we've already seen. That's when you say that the tables have rows and columns and that a table is a set of rows, right? So this is a model. We're going to see that there's models for trees too, for XML, JSON, and so on. Graphs and cubes, we're not covering that, but there are models too. Then we'll validate data. Validate data is because of the big mess, right? In a relational table, it's already valid. You already know that in every column you have the same types, right? But if your data is in a big mess, then you need an extra step that we didn't have in the 70s. And the extra step is about validating the data in XML, JSON, and so on and so on. So I'll tell you how we validate trees, AKA fix the mess and prepare it for machine learning. Then we look at how to process data. MapReduce, Spark, maybe these are buzzwords that ring a bell. So I'll show to you how we let the data flow on these cheap machines in the data centers. So this is called data flow processing, Spark, MapReduce. We'll look into that. Indices that I promised to you, we'll look again into that to tell you how to accelerate things by building indices. Again, that's what you have at the end of the books with the alphabetical list of words. Data stores is the whole package. That's the piece of software that you sell or that you put for people to download and use. RDBMS is just Oracle, IBM, Microsoft, PostgreSQL. These are all the ones that are well known. But we look also in this course at MongoDB, which is an example of a tree-based system called the document store. But there's many, 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 many others, right? That you might have heard of. So we'll look at some of them. It's called the data store. It's not called a database because it's less than a database. So this is why we call them data stores, right? Then we'll see how to query data, mainly with SQL and JSONic, right? SQL for tables, JSONic for trees. And then that's not in this lecture, but the user interface is the final way you can give it to a user with a spreadsheet software, Tableau, and so on and so on. Now we can even speak to databases somehow, and that's also a voice interface. Okay, so that's the big stack that we are going to rebuild, but it's going to take us 14 weeks to do that. And we start at the bottom with storage right after the break. So I see you at 17 past 9 for the continuation of the lecture. Thank you very much. See you in a bit.